All right, let's talk about one of the most fundamental, most powerful laws in all of electronics. It's a surprisingly simple rule that's running the show in everything from your phone charger to the entire power grid. And, understanding it is way easier than you might think. So what is this master rule? Well, it's Ohm's law. And hey, if that sounds a little intimidating, don't worry about it. Seriously. By the end of this, you'll see it's an incredibly intuitive idea that explains so much about how our modern world actually works. Okay, so to really get a grip on Ohm's law, we first have to meet the three main characters in the story of electricity. These are voltage, current, and resistance. Just think of them as the key players in every single circuit out there. First up, we've got voltage. The easiest way to think about voltage is as the push, or the pressure in the system. It's the force that's just waiting to get the electricity up and moving. Without voltage, well, nothing happens at all. Next up is current. So if voltage is the push, then current is the actual flow that you get because of that push. It's how much electricity is actually moving through the wire. We measure this in amperes, or you've probably heard it called amps. And finally, our third character in this little play, resistance. Resistance is pretty much what it sounds like. It's the opposition. It's the friction in the circuit that tries to slow down that flow of current. We measure that in a unit called the ohm. So how do these three all relate to each other? Well, a guy named George Simon Ohm figured out that the current is directly proportional to the voltage. In plain English, the more you push, the more flow you get. It makes perfect sense, right? But, and this is a huge but, there's a fascinating catch hidden in that fine print. This only works if the temperature stays the same. Just remember that little detail because it's going to be really important later on. Now look, since we can't actually see electrons zipping around in a wire, the absolute best way to visualize all of this is with a super simple analogy that everyone gets. Just imagine water flowing through a pipe. In our analogy, voltage is exactly like water pressure. I mean, think about it. The more pressure you have in the system, the harder the water is going to spray out of the hose, right? It's the same thing with electricity. Higher voltage means a stronger push. And the current, well, that's just the flow rate of the water. How many gallons are actually flowing past a certain point every minute. It's the volume of electricity that's on the move. And this is where the analogy really clicks into place. Resistance is just like the width of the pipe. A big, wide pipe has really low resistance, right? It lets a ton of water flow through super easily. But if you try to force that same amount of water through a tiny, narrow straw, well, that's high resistance. You're restricting the flow. This is a perfect picture of how electrical resistance works. Okay, so we've got the concept down. The push, the flow, the opposition. Now for the really cool part. All of this entire relationship can be described with one beautifully simple and incredibly powerful formula. Now that we have the water pipe idea in our heads, the math is going to seem like a piece of cake. Yep, this is it. The whole thing in 3 letters. V equals I times R. Voltage equals current multiplied by resistance. Seriously, this simple little formula is the key that unlocks how we analyze and design just about every electrical circuit. And you know what? There's a super easy trick to remember it and rearrange it. It's called the magic triangle. If you want to find any of these values, all you have to do is cover it up with your finger. So let's say you want to find voltage. Cover up V, and you're left with I next to R. That means you multiply them. Need to find current? Cover up I, and you see V over R. It's a fantastic little cheat sheet. Now, this table shows something that is absolutely crucial. For any given conductor, like a simple resistor or a piece of wire, its resistance is a constant value. Look at this. Even as we crank up the voltage from 30 all the way to 70 volts, you see the current goes up right along with it. But when you look at the ratio between them, V divided by I, it always comes out to the same number, 10 ohms. That consistency, that right there is the very heart of the law. Okay, that's enough theory for now. Let's put this thing into action and see how this law helps us solve a real practical problem. So here's our scenario. We've got a standard 220 volts outlet, and we plug in an electric heater. We know that the heating coil inside has a resistance of 100 ohms. The big question is, how much current is actually going to flow through it? Let's break out our magic triangle again. We're looking for current, right? So we cover up the I, and that leaves us with V over R. So all we do is plug in the numbers we know. That's 220 volts divided by 100 ohms. And boom, there's our answer, 2.2 amps. It's as simple as that. See how powerful this is? Ohm's law lets us predict exactly how a circuit is going to behave before we even turn it on. It's incredible.
And you knew there was a but, right? Here's where things get really, really interesting. Because Ohm's law, as powerful as it is, well, it can be broken. There are important everyday situations where it just flat out doesn't apply. Hey, remember that little phrase from the official definition way back in the beginning? Provided the temperature remains unchanged? Well, it turns out that isn't just some legal fine print. It is everything. For Ohm's law to actually work, the temperature of the thing carrying the electricity can't change in a big way.
This means the law totally falls apart for components like diodes, which only let current flow in one direction, or for semiconductors, the brains inside all of our modern electronics. In those things, the relationship between voltage and current just isn't a straight line. And, most importantly for our story, the law fails for any conductor that gets very, very hot. And here is the absolute classic example, an old-school incandescent light bulb. As that current rushes through that tiny little tungsten filament, it heats up to thousands of degrees. It gets white hot. And as its temperature skyrockets, its resistance goes way, way up too. This means that V divided by I ratio is no longer constant. So the humble light bulb is a famous violator of Ohm's law. So there you have it. Ohm's law, the simple rule that governs most of our electrical world, and the crucial exception, heat, that makes things even more interesting. Which brings me to a final question for you. Now that you know the rule and the major exception to it, what other devices around your home do you think might be secretly breaking this law?